Swayam Prabha. Digital India. Educated India.
Okay, we are discussing solid mechanics, and we have come to solid mechanics for the second time to understand displacement gradient. Okay. That was our objective, and the title for our second visit is deformation and strain. In that we have discussed the types of deformation, namely change in length, change in angle, and then we quantified them in terms of strains, namely normal strain, shear strain. Then we said the strains are related to the displacement of the particles or points. So, then we discussed what is the displacement field, what is the displacement gradient, slowly moving from 1D, 2D to 3D. Now, we have strain on one side, displacement field on another side, and then we will have to relate these two, and that is the objective of this lecture. Later on we will see what is components of displacement, and then the last bullet later on. Okay. The one question which I am going to answer throughout this lecture is that we are given displacement field, how do I calculate strain? Okay. That is what we are going to do now. Okay. This we have seen already. We introduced deformation, which are change in length, change in angle, and strain is a measure of deformation, which means that we first introduced change in length, change in angle, but we need to quantify it, and quantification was through strain, namely normal strain, shear strain. That is the meaning of the statement, strain is a measure of deformation. Now, when we explained even normal strain, shear strain, we said take some points in the object along one direction, and then the point got displaced, they moved to some other location, which means that the strain, deformation are all related to the displacement of points or particles in the body. We are going to derive a relationship for strain in terms of displacement field, that is the objective. Now, just to recall, we will discuss, our discussion is going to be in 2D. So, just to recall the discussion earlier, what is the displacement field? What is shown here? The red dots represent some points identified or particles identified in a plate, 2D plate like this, in the initial state and undeformed state. You apply a force, it deforms, go to final state or deformed state. The blue dots represent the same points in the deformed state, and then we said Ux represents the horizontal displacement, which is nothing but the difference in the x coordinates of the points. And if you focus, the difference in x coordinate, which is x displacement, keeps changing in the x direction, also in the y direction. Okay. And now, if you look at the y displacement, which is the difference in the y coordinate, that also changes if you go along the x axis and the y axis. Okay. That is what we summarized, that is what we discussed in this slide. Ux changes with x and Ux changes with y as well. So, Ux is a function of x comma y. Similarly, Uy changes with x, Uy changes with y, and Uy is a function of x comma y. Okay. And we have represented the displacement field in terms of a vector. U vector is equal to Ux I plus Uy j, and Ux, Uy themselves are functions of x comma y. Okay. That is a displacement field. We are given this displacement field, we need to find out the strains, that is the idea. Now, we are proceeding towards finding a quantitative relationship between the displacement field and the strain. Before that, what we will do now is qualitatively we will see how we can explain strain if you are given displacement field. Okay. We are going to derive quantitative relationship later. Before that, to get understanding, what we are going to do is qualitatively can I say whether we have strain or not, etc. Okay. So, let us start. We are given a displacement field. What is a given displacement field? Two dimensional case. So, we are given u x as a function of x comma y, u y as a function of x comma y. In this case, they are much simpler. The x displacement depends only on y, okay, and the y displacement depends only on x. Okay. Now, what is the functionality we have taken? We have taken u x as alpha plus beta y and u y as 2 alpha minus beta x. So, as I told you, u x depends on y only, u y depends on x only. Now, alpha and beta are constants, and we have a condition that beta is very small, much smaller than 1, okay, extremely small in fact. Okay. Now, how do you understand this? We have a plate as we have seen earlier, and we are given the displacement field for this plate. Okay. Now, in all these diagrams, what you will see is the red boundary represents, the red figure represents the initial configuration or undeformed configuration, and the blue figure represents the same plate after deformation, the final state. Okay. Initial state, final state, red is initial state, blue is final state. Okay. Now, for the moment, for the first case, we will take alpha equal to 1, beta equal to 0. Let us see what happens to the plate. We have taken alpha equal to 1, beta as 0. Now, when I say what happens to the plate, what I mean is given the coordinates a, b, c, d, I want to find out the new coordinates a, b, c, d. Okay. Initial coordinates are given, final coordinates have to be found out. How do you find out? You take the coordinate, add the x displacement, add the y displacement, get the final coordinate. Now, but that displacement depends on x and y. So, accordingly you should calculate the displacement. Let us see one example. X final is equal to x initial, okay, plus u x as a function of x comma y. Y final is equal to y initial plus u y as a function of x comma y. So, that is what I said, final coordinates are equal to initial coordinates plus the displacement in the respective directions. Now, let us take an example, coordinate c. Let us see what is initial coordinate. Initial coordinate, both in this diagram both are superimposed. So, the coordinate of c, the initial coordinate of c is 1 comma 1. You see the final coordinate shown here, which is 2 comma 3. Let us see how do we find out that. Okay. Now, c 1 comma 1 moves to, I used arrow mark to show that it moves to c. What is the coordinate? The initial coordinate 1 x coordinate plus x displacement. X displacement is a function of x comma y. What is the corresponding x and y here? 1 comma 1. So, 1 the initial x coordinate plus the x displacement, and x and y are 1 comma 1 here, because we are interested in finding out the new coordinate for point C. And now, what is the new y coordinate? The old y coordinate 1 plus the y displacement, but once again it is a function of x comma y. Where should you evaluate? At 1 comma 1. So, if you do that, the old coordinate, what is the displacement? You have to evaluate this u x at 1 comma 1. Beta is anyway 0, just a constant alpha which is 1. So, that is why it is 1 here. Now, let us evaluate this term u y at 1 comma 1, once again beta is 0. So, it is just 2 alpha, alpha equal to 1. So, you get 2 here. So, the new y coordinate is the old y coordinate, it is 1 plus the vertical displacement 2. So, now what is, if you sum up, the new coordinates are 2 comma 3, and that is what is shown here. So, likewise we can calculate for A, B and D, and you can draw the it's a square here connecting A, B, C, D, which shows the new coordinates of A, B, C, D. Okay. So, what is that we have done? We are given displacement field in terms of ux and uy. In this particular case we are taking beta equal to 0, alpha equal to 1. We are given the initial coordinates. Using the displacement we found out the final coordinates. Now let us see what has happened to the plate. The plate, if you see here, has just moved from one location to the other, it has just got displaced. If you look at the length of all the sides, there is no change, which means there is no normal strain. If you look at the angle, there is no change, there is no shear strain. Okay. So, it has just moved from one place to the other place. The technical terminology for this is translation, that is why the title says translation. The plate, you applied a force, it just moved the plate, that is all has happened. Okay. Remember first slide we had change in length, change in angle, we had also said plate is also moving. We ignored that point of time. Now we are discussing that by applying the force, nothing has happened to the plate in terms of shape or length or angle, nothing has happened, it just moved. That is why we call it as translation. To be more specific, we call this as rigid body translation. Why? Just like a rigid body, it just moved from one place to another place, and you do not see any change in length, any change in shape, which means no normal strain, no shear strain. Okay. Okay. And now we will also introduce one more terminology called rotation. There is no rotation also, the plate was like this, it just moved, and one way to assess rotation is based on the diagonal. So, if you look at the diagonal, there is no change at all. So, to conclude this case, alpha equal to 1, beta equal to 0, the plate, remember there is displacement because all the coordinates have changed, but the displacement is because of translation. Okay. And there is no normal strain, no shear strain, no rotation. Okay, the simplest case. Now let us take a more realistic case where there may or may not be normal strain, shear strain and rotation. Okay. Now same displacement field, we will consider now two cases. The slide is split into the two columns. Let us discuss the left hand side column. Same displacement field. Now I take alpha equal to 0 because we have seen it just translates, no other effect of alpha. We will take beta as 0.05. Remember beta has extremely small value, order of 10 power minus 6. Why is it so? We have seen that if you apply any force on a solid object, almost rigid, a small deformation happens. Okay. So, slightly deformable. So, beta is very small, we will take, but if I take beta 10 power minus 6, hardly we can see anything. That is why we have taken beta as 0.05, but remember beta 0.05 is a very large value. To show clearly, we are considering beta as 0.05. Now let us proceed. As we have seen earlier, the red figure represents the initial configuration, the blue figure represents the final configuration. As we have done earlier, when to know the final configuration or final state, I need to calculate the coordinates. Let us see how do we calculate. C 1 comma 1, once again we will consider C, and it moves to, how do you find the final coordinate? The initial x coordinate plus the displacement ux, and then ux a function of x comma y, I need to evaluate at 1 comma 1. So, this one represents ux at 1 comma 1, and if you evaluate alpha as 0, beta is 0.05, multiply by 1 gives you 0.05. Now come to the next y displacement, the initial coordinate. Okay. What is the y displacement? This represents uy at 1 comma 1, alpha 0. So, it is minus beta x, x is equal to 1, giving you minus beta, which is minus 0.05. Okay. So, the x coordinate is old y x coordinate 1 plus x displacement evaluated 1 comma 1, which is beta, which is 0.05, y coordinate is old y coordinate 1 plus the y displacement evaluated 1 comma 1, which is minus beta, which is minus 0.05. So, if you evaluate, the new coordinates are 1.05, 0.95 and that is what is shown here. Look at this, slightly outside of 1 which is 1.05, slightly below 1 0.95, that is how you find the coordinates of C. Similarly, find the coordinates of B, A and D. You can draw the figure in blue, which is the final state. So, red represents the initial configuration, blue represents the final configuration. Now, let us analyze what has happened to the shape. If you look at the length, there is no change in length. What do we mean that by that? Focus on the initial AB, you have A here and then this point, that length and this length of this blue are almost same, or they are same. Here because I have taken 0.05, it may look like there is a change, but remember beta is extremely small value. So, there is no change in that length, which means that there is no normal strain. Similarly, if you take A and D and then AD, once again there is no change in length. So, there is no normal strain along x axis, along y axis. Now, what about shear strain? Look at the angle. Initially your plate was like this, the angle was 90 degrees. Now, after the in the final state, both lines have slightly moved this way, but their angle is still 90 degrees. Look at the angle between red lines, they are 90, angle between the blue lines are also once again 90 degrees. So, which means that there is no shear strain also, but look at the plate. The plate has undergone a rotation. How do you understand? As I told you, look at the diagonal, the red diagonal versus the blue diagonal, it has rotated clockwise. So, there is rotation. So, the plate was like this, small rotation, and the final configuration is rotated with reference to the original configuration. Final state is rotated with respect to initial state. So, to conclude, there is no change in length, so no normal strain, and then there is no change in angle, still 90 degrees, no shear strain, but the plate has undergone rotation. So, there is rotation. Now, consider another case, the right hand side, a slightly different displacement field. Why is it slightly? You will understand. Ux is given by the same expression, alpha plus beta y. Uy, instead of this minus beta x, I will change it to plus beta x, plus beta x. Now, let us see what is implication of this. Once again take alpha equal to 0, beta 0.05. Now, as we have done earlier for the left hand side, we will find out the new coordinates of point C. Let us find out this coordinate. Same like last time, 1 comma 1 is the old coordinate, 1 and then 1. To that you add the displacement. In the displacement along x direction is ux and is evaluated at 1 comma 1 and alpha 0. So, result in beta which is 0.05, which is same as last time. Okay. So, this represents ux at 1 comma 1. Now, y displacement, what is the y displacement? This is uy evaluated at 1 comma 1 alpha 0, which is now beta plus beta, and that is why you have plus 0.05. So, now the coordinates are 1.05 and 1.05, that is what you see here. In the earlier case 1.05 and 0.95, but now 1.05 and 1.05. Now, let us similarly you can calculate for A, B and then D. Okay. Now, let us see what happens in terms of strain. Look at the length, there is no change in length. If you compare AB and red AB and blue AB, no change in length. Consider let us say red AD and blue AD, once again no change. So, normal strain is, there is no normal strain. Now, look at the angle, BAD, the initial state 90 degrees. In the deformed state, look at the angle BAD, is a smaller angle, angle has reduced, which means that there is shear strain. In this particular case, we said shear strain exists when there is a change in angle. So, in this particular case, the because the angle has reduced, there is shear strain. Now, what about rotation? How to analyze rotation, how to view rotation? Focus on the diagonal. and the red diagonal, blue diagonal are just superimposing on each other, which means there is no rotation. So, the second case there is no normal strain, just like the first case. First case there was no shear strain, it just turned like this, but in the second case, the first case just turned like this, in the second case it has become like this, closer to each other slightly, very slightly. So, there is shear strain. First case just rotated, second case it was symmetric, remained symmetric. See, it is 1.05, 1.05, so along the same diagonal. So, there is no rotation. Now, going back to the objective, what did we say? Given a displacement field, we should be able to tell about normal strain, shear strain and rotation. That is what we have done, talked about translation also. Now, what we have done is qualitatively we have told by demonstration, finding out coordinates, looking at the picture, looking at the figure, etc. We are going to do this quantitatively, that is what our objective is. Okay. So, very nice example, very simple example from the book Raymond Parnas illustrates our objective very clearly. Before proceeding to quantitative evaluation of the expression, we are going to now find expressions for normal strain, shear strain, that is all, but this cases really illustrate what is that we are going to do. In fact, after deriving the relationship, we will come back to this example and then say, here we have said rotation, yes, but what is the value? We will be able to quantify it. Right hand side we said shear strain is existing, there is shear strain, but later on after deriving the relationship, we will be able to quantify it, find a value for that. Okay. That is what, anyway no is anyway 0, that still remains. Okay.